All right. Hi, everyone. Thanks for coming to this talk. My name is Zysolt, and I want to talk to you about model-driven navigation. I work at Bumble, where we have large code bases and several developers. We kind of always felt like that the mainstream approaches available for navigation and application structuring just don't scale well beyond medium-sized applications. And if you have a large enough product, then it can be a source of a lot of pain and frustration. So today, I want to discuss a couple of ideas how to take some of that pain away and make navigation a joy again. I also want to say that we recently released our navigation library called Epics, and its capabilities overlap a lot with some of the ideas that you will see here in this talk. But instead of doing a library demo today, what I want to do is to focus on the ideas behind it and why anyone would come up with such a library in the first place. So if I talk to developers, then there are some easily identifiable problems with navigation. For example, navigation does not feel like a first-class citizen. You don't do it directly from code, either from XMLs or strings, or using code generation for that. And most probably, you'll be using instrumentation testing to test your navigation instead of being able to do it directly from a quick unit test. Shared module navigation dependencies can be a lot of pain. And overall, there's this feeling that setting up navigation requires a lot of boilerplate. But not everything is so easy to identify, and yet they impact us. For example, I think that we have a quite screen-centric approach to navigation and application structuring, which is not a big surprise, considering that this is one of the first things that you see when learning Android in the official guides, is that teaches you that one screen matches to one activity, or later that one screen matches to one fragment. The problem is that, as I said, when you work on large enough applications, then at some point there's just so much complexity that can end up in a single screen, is that if you have this one-on-one matching to fragments or activities, then sooner or later this becomes very relatable and you find yourself fighting through thousands of lines of code. And you're not going to be having a good time. Stemming from this screen-centric approach, most probably we will end up using different mechanisms for navigation. So for example, for a screen-to-screen navigation, most probably we'll be using a backstack. Inside a screen, we'll probably use something like a view pager or custom-built libraries. But not everything is size of a screen or smaller than a screen. There are things also larger than a screen. And we tend to not even have a representation and navigation for multi-screen flows. So for example, if I have a registration or an onboarding where I have multiple screens, then that is really inconvenient to represent in navigation. Also, I might have entire scopes in my application, like my logged out scope or my logged in scope. And we don't really have a good enough representation of that. And even for those parts that we do have, we tend to end up having different solutions with their different APIs. Most of them usually don't allow us to extend or modify them, and they behave as black boxes. Which is a problem because navigation is stateful, but then this state is not under your direct control. So for example, an activity stack or a fragment manager or any other custom solution will have its own internal state, which contributes to the entirety of the application state. But that is separated from your business logic. And with an analogy, what we had before Compose is that a similar situation with the view hierarchy, in that you wanted to represent some of the view-related state in your business logic, but then the view hierarchy has its own internal state. And then you end up duplicating some of that state and try to synchronize between the two. And then Compose comes, and among many other things, there's this huge improvement that now you have this single source of truth in which it makes you able to define a state which becomes the state of the view hierarchy directly. And I just wonder, why don't we do that with navigation? Can we do that with navigation? So model-driven navigation would give you exactly that, the ability to define your navigation state directly. Compared to a UI-first approach to navigation, where you would navigate from a screen to a screen, with a model-driven approach, you would navigate to a state of the application. On top of that, I want to show you today an approach which improves in many of these pain points that we mentioned before. A solution that feels like first class again, directly from code, with type safety, without boilerplate. A solution that is easily unit testable, that is completely screen agnostic, which provides you a single abstraction to come up with any number of navigable components, where the state is directly yours to define, and it directly defines navigation itself. So what we're going to do today is we're going from 0 to hero, and we will build a conceptual solution in a couple of steps. We'll start with something very simple. Just see how we could theoretically navigate from code. Building on top of that, we will find a useful representation for navigation state, which will allow us easy unit testing, and the next step of building our backstack mechanism for screen history. And then we will add some beautiful transition animations. And here, this is kind of a convenient baseline package. But we will push the boundaries further twice. So building on top of this, at step 5, we will see what model-driven navigation actually is in practice. And then we will push the boundaries further even more by making this navigation composable. Let's start with navigating from code. So what you see here is just pseudocode, and it's just illustrating an idea in that you would have something like a screen, which is wrapped in a composable view. And then you could have a couple of implementations of that. For example, a home screen or a search screen, each of which has their own business logic. Now, with the search screen, there's one important detail in that it has a navigation argument. What kind of search text do you want to show the search results for? And it's represented directly as an argument. So then, in some kind of main part of our application, we could have a mutable state holding any instance of the screen, and then offering some API for that. We could change what's inside that. And here we can pass navigation parameters directly from code. And then whatever instance is held inside current screen mutable state, that gets composed into our UI. Awesome. This is absolutely bare bone and simplistic, but what we already see is that we can definitely do things directly from code without XMLs or strings with direct passing of arguments. So this is probably a good direction to dig more into. Finding a useful representation for navigation state. Why would we want to do that? It's because up until this point, it's only you, the developer, who knows how to create any actual instance of a screen. But with any decent navigation solution, you want your navigation library to be able to recreate these instances. Why? Because you might have a save restore cycle. Or you might have a backstack, and once you want to restore something from backstack, you want your navigation library to do this for you automatically. So the problem is now it's only you who can know how to create any of these instances. So we must find a way to make our navigation library able to construct this for us. If we go down the route with fragments or fragment managers, then we run into a similar problem if you represent our navigation targets, for example, with numerical IDs, is that a fragment manager can host any fragment that you can create, but it doesn't know how to create them. So as a consequence, you end up with zero-argument constructors, or if you are going with fragment factories, then you can't pass dynamic parameters. Why? Because a fragment factory implementation lives in a separated part of your application from the call site when you want to use it. So what if instead we made a deal and we said that our navigation manager solution would only be able to host and create a subset of all these possible things? What would that give us? So for example, in code, we could say that our navigation manager implementation is typed to this navigation target Zysolt class, representing with a Kotlin object our home screen, and a data class for our search screen. Now, we would have this resolve method, and the job of which is to resolve any of the Zysolt class elements to actual screen instances. And the important part here is that now the framework can run this code, and using the exhaustive when expression, it can actually expect us to define how any of these navigation targets resolve to screens. So you as a developer can define if it's the home, then this is how I construct my home screen. So you as a developer gain the ability to use any kind of constructor that you want. So what we lost here now is that we cannot host just any instance of a screen, like with fragments. But is this really a loss? And I want to say that I don't think so, because based on your product definition, you always know where your application can navigate to. So it's fine to use a finite set, but what you gain instead is that now it's you in the client code who can create the instances of these screens with any constructor that you want, and you can directly use dynamic contextual parameters at the call side. The other benefit is that now we have this enum or sealed class representation of our navigation target. Then we can have a kind of a backstack, just passing this token into it as an initial element, and after doing some operations, we can assert that the current navigation target in our backstack solution is this other instance of a navigation target. And what you see here is actually a very simple unit test, so we didn't need to fire up instrumentation to run this, and that's a huge win. But there are more wins with using this approach with sealed class elements. And this leads us to creating a simple history. So for example, I could say that I have 4 possible navigation targets, A, B, C, and D, and I already define how those map to screen instances. Now what I can do is I can say that I want to build a list of them with a rule that whatever is the last element in this list is considered active to be on screen, and everything else is considered history. So as the list changes, our navigation solution would just remove whatever is no longer active and compose into the composition whatever is now active. The huge win here is that we can now implement a backstack with only list operations. So for example, a push operation just becomes adding a new element to the list. Super simple. Replace is equally simple. But you can go further. Any kind of complex history operation you can do with simple list manipulation. For example, discarding your entire history or implementing a single top-like mechanism. And I will be using illustrations moving forward in the following slides like this. So what you see here is that there are some numbers ticking on these colorful panels. And this is just to represent that we have something like an actual business logic ticking these numbers so that what you see are not just static views. But at this point, what you see here is that we have our simplistic backstack implementation. So when the buttons referencing push and pop are pressed, then the composition changes live. But it's not really beautiful, is it? Because it just swaps these screens. So what if we made it a bit more fancy and adding transition animations? Fortunately, Jetpack Compose comes with a lot of firepower, visualizing and animating things. And one of my favorite APIs is this update transition. So in the official docs, you have this example where you define 2 possible states for your box. It can be either collapsed or it's expanded. And then you run a transition on it. And then you associate this states to, for example, different sizes of rectangles or different sizes of border width. And then Compose does the rest for you. It's a super powerful animation API because it's you, the developer, who can define whatever state that you want in this enum class and whatever UI properties you want to match it to. So how can we apply this to our simplistic backstack solution? Is that we can say that each of our elements in the backstack can be at any given time in these 4 possible states. They're either created or active or stashed or destroyed. And the relationship is such as when they are created, they should transition to the active state. They can be stashed and unstashed, and they can become destroyed. How would our operations look like? So for example, with a push operation, if we have 2 elements in our backstack, then one of them surely is stashed, the other one is active. Then we should add the new one with the state of created. And now 2 things must happen simultaneously. One, the created should become active, and the currently active one should become stashed. And these 2 things run as 2 parallel transitions. With a pop operation, the active one should become destroyed, and the last stashed one should become active again. And again, this is happening in parallel. And after the transition finishes, we could do some housekeeping, and we could remove the destroyed element entirely. How does that end up in the UI? Is that we would now need to associate this to UI properties. And for example, we would animate a float based on this state towards 1, which represents 100% visibility or in any other case, if it's not active, to 0. And then we apply an alpha modifier to our composition, which gives us this nice and easy crossfade transition. Why is it crossfading? Is because we just said that two things happen simultaneously. Whatever becomes active is now associated with 100% visibility, and whatever was active is now fading out to 0. Can we do, for example, a slide? Of course we can. Instead of alpha values, we could say that we associate our sliding transition with offset modifiers. We could say that whatever is on the screen has 0 offset, and then we can define offsets to the left or to the right of the screen. And now we associate our states to these offset targets, which gives us this classical slide transition. But we need not stop here, because we can make it a bit more crazy and fancy and spice this up. So for example, what if I want to associate material design colors to this state? What if I want to associate rotation values to it so that the last state, the destroyed state, becomes rotated by 90 degrees when I reach that state? What if I want to do all of that? And I end up with a solution that is having sliding and color transition and rotation when the element goes popping to the destroyed state. That's pretty awesome. Because the win here is that we can animate absolutely anything that is representable by a compose modifier. And the other big win is that now we can replace the visuals without having to change the underlying model. So what we have here now is, let's put things into perspective. We are still building something from 0 to hero. And what we have seen so far is we can do stuff from code. We can find a useful representation of navigation state, making it able to be easily unit testable, build a simple backstack, and now we've just given our solution the ability to have beautiful transition animations. And this is kind of a baseline package. It's convenient, but now it's time to push things a bit further, and let's see what model-driven navigation means in practice. So up until now, we've been thinking in different navigation mechanisms. So for example, screen to screen, you would most likely use a backstack. Or inside a screen, you would be using a view pager. Or any other kind of custom navigation behavior. For example, in Bumble, you have swiping dating cards. Then you would either build a custom tailored solution for that, or you would try to find one, and each of which are separate solutions. So the question here is, could we find a simple single model that could describe any of these mechanisms? Let's call this abstraction a navigation model. And the navigation model's job is to answer the question, what navigation target is in what state currently? So for example, we could say that our navigation model has an observable flow of elements with the type of navigation target association to state. And then as a separate concern, we could have a transition handler mapping these states to actual compose modifiers. And coming up with any actual implementation of this navigation model would be a 3-step process. First, we would define possible states. Then we would define operations how to change this state. And then we would associate this model with UI properties. For example, putting things into perspective, this is actually what we have done now with the backstack, in that we have defined our possible states. We have defined a couple of operations, how those change those states. And we have associated this to alpha values, or we have associated this to slide and color and rotation. So how is the navigation model of a view pager any different? With a view pager, you do not have the concept of stashing and popping. So what you have is something which is active on the screen, something which is relatively before or after that element. And instead of push and pop operations, you would have next and previous operations moving this active flag around this list. And then with a similar sliding offset association, boom, you have instead of a backstack, now you have a view pager with the same approach. But this is really just the beginning. And with this navigation model approach, you can do a lot of things because it's abstract enough to be able to describe anything that you can think of. And I have a couple of examples to show that. So for example, with the backstack, I can say that I modify the underlying model so that it has more than one possible active state. And then associating those different active states to different offsets, I can have something that looks and feels like a card stack. Or I can say that all of my navigation targets are actually on the screen, and I associate normal and selected and destroyed states with them, with some scaling, offset, and rotation, so that I can make something where I can select, for example, profile cards, and I can just destroy them flying off the screen. I can also implement my own model by different states associated with different sizes, and I can make it full screen. How cool is that? I have a model becoming full screen. Or I can have this crazy example with this promoter carousel, just having various distinct steps with scale and angle and rotation using this profile card. And then, speaking of profile cards, how could we implement a profile card swiping-like mechanism in Bumble, for example? So what you have is you always have a top card, because as soon as you start swiping it off, the bottom card is now visible. So we can represent that in our enum class. We have a bottom and a top state. Also, when the top card is transitioning to either a liked or a pass state, we can represent that in our enum. And last, we have a queued state. So how these relate to each other is that once the top card moves to a liked state, then the bottom card should become the new top card. And whatever is in the queue becomes the new bottom card. Now, step 3 would be associating this to UI properties. So what I can do is I can say that the bottom card has only 85% of a scale of a top card. And when the model transitions from bottom card to top card, then it feels like it's coming into your face. And then the pass and like states I could associate with plus and negative rotation and offset, which gives you this nice swiping-like animation. It's beautiful. And this is a game changer in its implementation cost, because this 3-step process is super economical to make happen. Defining an enum is practically less than a minute. Defining these operations and then defining related associated compose modifiers is maybe 1-2 hours each, depending on how much complexity and how much UI experimentation you want to do. But overall, you can make something like this happen in a couple of hours. In fact, I've done this example from scratch in the matter of maybe 2.5 hours. And the other game changer is that now we have a very different perspective, because the screen becomes fluid. So previously, when you were navigating, then you had one screen with its rigid boundaries, and then you had another screen, and then you had navigation. And if you wanted to animate things, these were 3 distinct things to animate. Now what you have is that all of the 3 things come into the same single space. And now you can kind of compose whatever is on that screen, but the screen itself loses its hard boundaries. And it becomes like a viewport. So how do I make something feel like a screen? It's just by stretching an element with a modifier to fill the entire available screen space. And now it feels like it's the screen. But I can also do something of the opposite. So I can say, what if I downscale things that feel like a screen, and now they are something less than a screen? And I have an example of that with this example that starts as a standard view pager, but then it becomes a carousel. And then after a couple of rotations, it becomes a view pager again. That's super cool. And this is done merely by adding a new state representing any of the carousel positions. So what we have now is an approach that does not have the concept of a screen built into the model. And this leads us to defining model-driven navigation. Because what we see here is, even though you have these beautiful animations run by Compose, the point here is that we are not animating things, first and foremost, but we are describing something on the model level. And animation is only a consequence of that. So when I had these labels describing the possible states of a backstack, created and active and stashed, these are just abstract labels. These are just concepts. Nothing in that speaks anything about the screen or the UI. It's up to interpretation. Also, there's this parallel that if a view model describes the state and the behavior of the view, now you have something which describes, on the model level, the state and behavior of navigation itself directly. And this leads us back to our illustration from earlier. Now we have exactly achieved this, what you see on this illustration, in that now we have a navigation model as a single source of truth, which you can directly control from your business logic, and that becomes the state of navigation itself. And lastly, this is a very versatile approach, because with this single abstraction of a navigation model, you can do endless amount of navigable components. It's only limited by your imagination. You can have backstacks, card stacks, tiles, dating card mechanisms, anything that you can think of, and all of this in a matter of a couple of hours. But how do we do an app? Because surely a single model won't be enough for the entirety of our application. And this leads us to composable navigation. So if we have many, many, many screens in our application, and we would imagine that we would have one main navigation model for that this is really not scalable. So instead, what if we tried to make it composable and change our definition of a screen into a definition of a node? With the important difference here is that a node has the ability to reference any number of other nodes as its children, and then you can repeat this pattern. So what that gives us is a kind of a tree hierarchy. So that, for example, I can say that my registration flow is composed of individual registration screens. Similarly, with an onboarding flow out of individual onboarding related screens. And I can say that the main part of my dating application is composed of a dating, a messages, and a profile screen. But I can do something even crazier, and I can say that I want to represent my scopes, and I want to say that the logged in part of my application is composed of onboarding and main, and the logged out part of my application is composed out of the login screen and the registration flow. And there's this analogy with a composable UI here. And it feels kind of the same in that you can build more complex things out of simpler things. But there are some key differences. For example, this approach does not stop at the UI level. So what I have now is the ability to represent entire multi-screen flows or even scopes of my application, like being logged in or logged out. And the other difference is that this definitely cannot be static. So imagine if all of this is active at the same time, then what does the user see on the screen? So we want only parts of this tree to be active at any given time. And we can do something like defining an active path and say that whatever that active path touches means, in the end, what is visible on the screen. And we can change this activation path, and doing that will feel like navigation to the user itself. So after onboarding finishes, it goes to the main section for dating. And after, for example, someone presses the logout button on the profile page, boom, with a flick, we can go back to the login screen in the logged out scope for our application. That's pretty awesome. The nice thing is that we do not need to pick the whole path altogether. We can stitch it from these segments. And this is where our navigation models come really handy, because we can say that we can have a different navigation model on each of these levels. And I can say that I want to use this card-like mechanism that I just showed the other minute in my dating section. But even my dating section is only one of the possible navigation targets in the backstack of the main. And then I can say that I want to use different mechanisms. And for example, in registration and in onboarding, I want to have a view pager-like mechanism because I want my users to be able to go back and forth in those screens. And in other parts of my application, maybe I want to use something like a backstack. But even if you have multiple instances of the same type, they are different in that each of these backstacks might have their own different histories. And you can have even different transitions associated with them. So one might be crossfading, the other one might be slide-in. And this gives us something new in that now we can not only navigate from screens, we can navigate in screen states as well with the same approach. And now we can navigate entire scopes of our application. And this truly gives us a way to navigate to a state of the application rather than to a screen. So that was a lot. Let's see what we have achieved and sum this up. So 1, we have improved on our common issues. Now we can navigate directly from code with a type-safe way, without boilerplate, with an easily unit-testable navigation. 2, we have gained full control in that we can define our own operations. For example, in the case of a backstack, with just simple list manipulation. We can define our own navigable models, not just the backstack. And we can use any kind of animation that we can think of just using Jetpack Compose modifiers. And 3, we have seen a paradigm shift, in that now we can navigate to a state of the application, where the screen only becomes a viewport instead of having rigid boundaries. We have seen how with a single abstraction we can have an endless amount of navigable components which are quick and easy to implement. We have seen how with composable navigation we can take this to the next level and describe the entirety of our application with this approach. Do you want to see a practical implementation of all of this? Well, you already have, because in fact all of the illustrations that I've used here were video captures of doing this actually with epics. And this is something that we just recently released and we are quite proud of. And we would love if you would take a look at it, because it gives you an easy, quick way to start using this and try this out in practice. So if you like it, do give us some feedback. And that's all. Thank you very much.